source code. All right, so there's another branch you say. There's another branch. All right, so maybe what we could do is we'll go through, let's see if we'll go through your, let's see. Oh, wait, we need to go over to your fork. We'll go over to your fork. Minimal is the best by far. All right, let's go to minimal. Let's go to minimal. All right, so I want to go to pull requests, and we'll go over here to heat map, and then we'll click on your version over here, and then we go to minimal. Excellent. And then what I'm going to do is we're going to go ahead and clone your repository, and we will load it locally. And we'll say over here, we'll just do this. Git clone cd click. Oh, that's excellent. There we go. There we go. Okay. Close this. CD. Hey, how's it going? Just a random. How's it going? Hey, we're going again. Feels so heartwarming to see you. Where are we at here? So let's do Python main. All right, let's see what this looks like. All right, let's see. All right, here it goes. It's off to the races. Oh, hey, we're getting some jump arounds there. We're getting some jump arounds. Is it working? Is this, I'm on the minimal branch. Is this the right, does this look correct? Does this look correct? I think it does. It looks exactly the same as it, wait, is this even the right, is this the right one? Hold on a second. Yeah, this is, so git status. Oh, wait. We need to check out the branch. Git fetch all. Git checkout origin minimal, right? Git checkout -b minimal. Excellent. All right, now I was like, this looked like it used to be before. I'm like, I'm not noticing anything different. It's because we were on the branch. Git status. All right, git branch. All right, so we are on the minimal branch, as you can see here, right here. Minimal branch, right there. Minimal branch. Okay, let's try it again. No, you made a new branch called minimal. Oh, I did. Well, that's actually fine. That's actually fine because I did pull it. So git log. Here you go. Here's your log. So this shows us that we're on the correct place right here, right? This looks correct. Stabilized lost, more models, adjusted learning rate. Let's validate this. Let's look this. So this is the minimal branch, and we'll look at all the commits. Let's see if the messages are right. Stabilized lost, more models. Yep, there we go. We're on the right track. Yes, that's the one. All right, we did it. We're there. We're making things happen here. All right, so let's try it. Python main run. Okay, pull it in. All right. Oh no, instant failure. Cannot convert MPS tensor to float64. D-type on MPS framework doesn't support float64. Please use float32 instead. Okay. Solved. It might be. We just have to do a little bit of change to work on my particular accelerator. We have to make some changes on my accelerator. I need float32. Float64 is too much. All right. So let's try this. Main float64. And we'll just change this to 32. Is that going to do it? I don't know. Oh, just remove it. It's fine. All right. Yeah. We'll see. I'm pretty sure that's all we got to do there. Ooh, the click is actually going. Oh, look at that. Oh, look at that. Ooh, look. Ooh, this is great. This is great. Oh, wow. Look at how good that is. Okay. You can visually see that it's looking pretty good. It's looking pretty good. See where the magenta dot is actually going underneath. We need to make the magenta dot bigger so we can more easily see it, because now it's actually going underneath the click locations. Walking through Neva's source code for the AI click predictor, and it actually works now. It actually works. It actually is predicting where the UX user is clicking. And today the plan is we're going to walk through all the code. Obviously, it's broken right here, so we're gonna make a few changes. Oh, Steven, doing rookie mistakes? Yeah, I know. You want to install 3.12 on all the Pytorch projects. Okay, 3.12. Got it. Good news. I already have it. Source venv 3.12. I've got it already. Bin activate. Oops, no, activate. Activate, thank you. Okay. And then pip install torch and torchvision. I think that's all we got to do. All right, looks like we're already satisfied. Let's try running it. Let's see if it works now. Oh, pygame, we got to do that, pygame. Pip install pygame. Okay. All right. Good news. All right, let's see if it runs now. Let's see if it runs. Hey, it's looking good. It's looking, maybe. It's compiling. Okay, it's compiling. I'm pretty sure it's compiling, right? It's doing all the things to make it faster. Let's see if it's looking good. Is it running? I can't tell. Is it working? I don't know. Oh, there it goes. There it goes. Okay, good. All right. It, for whatever reason, actually seems like it's a lot slow. Well, okay. It seems like it's the same speed as it was before. Oh, although the clicks are doing pretty good. Look at those clicks. Look at those clicks. Look at the clicks. Oh, that's so good. Oh, the tracking is just about almost spot on. All right, it needs more. Steven, what's your resolution or plans for this year? Well, what's our definition of done? Maybe we can see some similar data sets, slow motion play to see ourselves, see how good predictions are. Yeah, so definition of done is when, after it's done training here, we will try some clicking patterns. And if it predicts my clicks, I think that counts as a win. I think it counts as a win. Hey, Ghost Wolf, how's it going? What's happening on the screen? So what you're seeing here, all the green dots are previous clicks, and the magenta dot is the dot that is predicting the next click. And you can see that very often it actually gets very close to where the click is supposed to be at, which is, I think, amazing. So this is Neva's code. We'll be walking through Neva's code. We'll see what changes were made and see maybe if we can increase the training, because I don't know how big the batches are. Hey, guess whose birthday is today, right? I know wait, is it Earth? Is it Earth's birthday today because of the new year? Is that how it is? Close the determine window or dropping the prints. The IO is slowing the display. Actually, the IO is not going too fast. I think what the slowdown is, Frankie, what is this? This is a click predictor. Where I click on the screen, it tracks where I'm going to click next. Oh, did it get it? So see how close it got? See how close it gets? It's doing pretty good. I think it's doing pretty good. Yep. It knows there. It knows there. Yep, it knows there. It's good. It's pretty close. It's pretty close. Look, isn't that good? It's like predicting where it thinks. See, that's pretty good. That's pretty good. All right, I count that as a win. Let's walk through your code, Neva. All right, so we've got a lot. All right, so we don't need to do the debugging code. We don't need to worry about those classes. We already have the draw. That's exactly the way it was before. We've got our heat map. We've got a skip net. Look at that. I don't know what you're doing to the skip net. That's kind of neat. Stage 1, stage 2. Concat dimensions. So forward, block 1, block 2. Concatenate the H1, H2, and X. Interesting. Self.head. What's this? I'm reading some oh, got it. Okay, so it's just a simple linear pass through. Okay. Concat dimensions looks good. Okay. We don't need to read that because it's not actually okay, so we've got a different skip net. Walking through Neva's artificial intelligent system that was written for click predictions. It does a very good job. Look at this. See that magenta dot and all the green dots are where I'm clicking? The magenta dot follows. It's pretty good. I like it. That's very satisfying. It's very satisfying. That's neat. Okay, let's keep going. Okay, let's walk through it. Okay. Super init, standard stuff. Input dimensions mod 2. So if it's X, right, it needs to be, this is great. That's a neat assertion. Did you put that in there on purpose for like, that's actually pretty neat. It needs to be even, right? It needs to be even numbered. So that's why you're saying, I'm actually kind of curious. I've never used 3 assert false, comma, interesting, comma, it broke. Okay, let's try that. Assertion error. So then we say assert true, and then it didn't break. Okay. That is, what is this? Torch arrange self timestamp slow. Okay. Cache sine cosine for exactly our length. What are you doing here? This is interesting. So is this some sort of mechanism that you're using to capture order, like time series? Is this what this is for? I'm not familiar. I know what this is. This is essentially going to draw a circle. I mean, you can get a circle. I know you could draw a circle using this. Oh, and then you register some buffers. Nice. the graph successfully without having to break anything. I like it. Similar to transformers, this is time encoding. Got it, time encoding. So it is. You are capturing the essence or the essentially the order of things. I'm actually kind of curious. What are your input dimensions? What did you set it to? What did you set it to? Here, I actually got a better idea. Let's go to skip net. You set it to input length. What is this? How big is input length? 8. Okay. Got it. Idea of periods. Very nice. Very nice. Thank you for walking through this. This is really exciting. We're learning a lot right now. A lot of the patterns humans do are cycles. They are circles. Yeah, they are circles, aren't they? Hey, Kyle, how's it going? Hola, ¿cómo estás? Good to see you. We are muy bien. We are muy bien. Hola. Hola. Okay, so you're using this to sort of represent time series. And here's our convolutional neural network. Your conv 1D. Hey, wait a second, Neva. I remember you mentioning conv 2D was required, and you got a conv 1D there. I'm like, hey, I wonder if we could use a conv 1D here. I was wondering. And we've got our time series, or sort of time encoding with each click. And I really want to see where this is going to be. I want to see how the math works here. Okay. So B is the shape. Okay. Forward, B shape. So X batch and then D is equal to the input dimensions. Okay. So of course you want the batch. Got it. Makes sense. Reshape B T for time steps. Okay. View sequences. Nice. I'm actually kind of curious to see what that looks like. I'd really like to see what that looks like. I mean, I can visualize it here. I know it's a 3D matrix. Essentially, though, batch, we don't care about the batch. We only care about this. So step dimensions is, what is this? This is 2? Is it 2? I think it was 2, right? It is 2, yes. Okay. All right. And then time steps is going to be 1. Is it 1 based on the math? Yeah, it's 1. So that's weird. That's very weird. See how that works there. No, it's floating head physics channel. I haven't heard about, and you saw that it was very simple explanation and fast. Nice. Very nice SAQ 3000. I like simple explanations. They're my favorite. Okay, let's keep going. Let's keep looking at the code here. Okay. So this will, let's go over here. Let's go click that button there. Okay. Steven, time steps would be 8 there and are 8 inputs. Oh, really? Okay. Because step dimensions, I was reading through this, and step dimensions I do believe is currently 2. Time steps is input dimensions. Oh, got it. And then input dimensions is going to be 8. I saw it. I saw it was 8. So time steps will be 4. So you've got 2 and 4. Got it. 2 and 4. Okay. So it'll be 2 and 4. So it's this very simple 2x4 matrix. Very simple 2x4 matrix. And the batch size, right? I'm pretty sure. Okay, let's keep going here. So then we use the registered buffers. Expand. So I'm not familiar with this. I do not necessarily understand what this looks like. I would very much like to print it out, though. So here's what I want to do. I want to rerun this code and print it at various locations so I can see kind of what it looks like. Although it is kind of being represented here, so you can kind of see that it's being represented there, right? V, there we go. Yeah, you can see all the dimensions here. And then you concatenate. So you add these all together. Really? This is neat. This line right here. I love it. This is, so you don't have a separate encoding anymore. You did not separate out the encoding. You just put it all in the forward function. This is all in the forward function. Skip net forward. Okay. So essentially this is you encoding. This is you're encoding it right here. Reviews. I know. Rarely do code reviews. I'm having a lot of fun with this. Skynet on the moon. I get Skynet on the moon. 1 hour for, to go for New Year. Other work. Hey, it's almost New Year, almost 2026 for you. For me, it's quite a while away. Although, technically, we're all on the same planet, going around the same spot, right? So it should be New Year everywhere, all at the same time, I think. It's an artificial human construct that we're doing it this way. It would be but constant, yes, but look what it's passed to. It's a convnet. Okay. SAQ. All right, so B times step. So yeah, a constant there. Okay, so this is a constant. So you got this sequence, and then you permute that. Okay. And then you put it through a conv. On your conv is going to be. Let me see what that looks here. I've got an idea. Let's bring this up here so I can see it better. Okay, here you go. Oh, you even have dropout. Interesting. I didn't know that you would add dropout. That's neat. Might as well. Kernel size, padding. Okay, so this is it going to be the same? So far, all this is the same. This to me looks like it's constant so far. Like everything calculated up to this point is always going to be the same for every input. Tell me I'm wrong. Tell me I'm wrong. I'm reading this, I'm like thinking, this is always going to be identical every single time. It's always the same. Pretty sure. Unless, the different batch sizes, I believe, because you've got a different batch shape there. Genetic testing with AI on the moon. Moonlings? Maybe. We could, right? So that would be a way to get around all of the, I guess, what do you call it? Laws? Like the laws and like legal requirements. The input X is different. So wait, did we, X. Oh, I got it right here. Okay. I missed that. Okay. Thank you. I missed this. So we're actually using the X data and we're putting over a view with the time step and dimensions. Okay. So we're changing the X. Okay. Got it. Thank you. Thank you, Neva. You corrected me. I see it now. I see it right here. So it's always going to be different. Every single input, wherever the click is going to be, it will be different. Okay. There. That's the key. That's the key. All right. I'm happy about that. I like it. I like it. Okay. Then we do a reshaping, which makes it into, it looks like a single dimension array. Is that what that does? It reshapes into a single dimension. One-dimensional array. Then you project onto the flat, which is interesting. So a lot of this, like I've never done this kind of I've never used these specific functions before. Usually when I'm trying to manipulate whatever the input's going to be, I do this all by hand. And all of these main functions do this slightly differently than I would do it. Just slightly differently. I read the article on symbolic. I want to see, and so what I want to do now is I want to start stepping through some of this. Let's keep reading. Let's keep reading, and then we'll start printing out some of the things I want to see. Okay, so all that's the same as before. Same as before. Input dimensions looks good. SkipNet, we got the SkipNet model. All right, that's pretty neat. I like that. All right, so instead of putting our model directly defined inside of this NN predictor, we set it up here. We put it up here, and now this has all of the things here, and then also has a forward separate from the predictor. But are you going to also have a forward in this though? I think you will. Okay, so you just got it. Optimizer looks good. Max samples, training data size. All right, sounds good. All the same as before. Okay, looks good. To device. Self, the entire self. Wait, what? You can do that? Wait, no way. So everything can go to device. You can do that? That is neat. I didn't know you could do that. Okay. I had it the other layers before. I think I removed that because it was good this way. Anyway, let's keep going. Let's keep walking through this code. All right, so where's X and Y being used? K, X, and Y. So K's here. Okay. So you're getting your features and labels. Straightforward. But then you say model.train here, which is what? Let me see here. No, that's within the class. All right. Then you've got these sort of like internal hidden functions that you're going to access later, which I assume you're going to say weighted loss insight. Yep, right there. Okay. Weighted loss. Torch. Shifts. Okay. Normalize. ABS. Clamp. So, see, right here, if you're clamping, I mean, can't we see, this is like also like, I was wondering if we could like, instead of like allowing things to hit 0 or get too large, I feel like we could do some sort of clamping or something like that tapers, like a normalization function or something. Obviously, like maybe an expanded version of like 10H or something. I forgot about that. Right. All right. So it moves it to training mode. So it doesn't actually train the model. It just moves it to training mode, which sets it up in a way that it allows things like this, right? The dropout. It allows the dropout layers to be active. And if you disable training mode, dropout no longer is being used in the feed forward neural network. So that's like noise. Add gradient noise. I saw this. And does it add a lot or a little? Oh, this also does checking here. So for all the parameters, if there is no gradient, you only do it to the gradient. So during the training process. Okay, that's interesting. I've never used that strategy before. That is pretty neat. G gradient, so you got the gradient. It's very moderate. I'm curious. I want to look at it. I want to look. So here's the noise, and then you're adding the noise. Couldn't you do like G plus noise? Oh, wait, G equals G plus noise, because it's Pytorch, right? It's kind of like, should this be able to work? I'm pretty sure. Or you can't do that because p.grad. So you'd have to say p.grad. P.grad equals p plus equals. Right? You could do something like a plus equals noise. I'm just wondering if that's also possible. No, because normal plus keeps gradient. Got it. Okay. Add will make it it permanently, so it's a mutation. You see the underscore methods used for gradients and parameters a lot. Really? Okay. All right. Like it might be fine. Actually, not sure. Okay, got it. Understood. I got it. Understood. I was kind of curious. Okay, so noise random. All right, so you get a random G, multiply it by 2, and then multiply it STD. What is STD? So let's see. Uniform. Okay. I'm curious about what STD is. Is it it should be a very small number, right? I'm assuming it's a small number to keep the noise pretty beefy or pretty lightweight. So let's see. WS. Let me search this. Oh, it's up here. It is a very small number. All right. It's almost like an epsilon at that point. It's very small. All right. Very happy with that. Very happy with that. Okay. So you add a very, very small amount of noise to the gradient. That is neat. That is very neat. I did not know that you could do that. It makes a lot of sense. And also, yeah, okay. Wait, this is weird. I mean, I feel like there's some counterintuitive action going on here. Torch with no gradient. Then you use the gradient right here. Like, you're straight up using the gradient right here. Like, what's going on? With no gradient, but actually, just kidding. We're actually using the gradient right here. What? That's so weird. Like it might be, it's 10% of the smallest learning, right? So it's not too tiny. Got it. All right. So it's a little bit tiny, but not too tiny. Fit. Okay. So you're training here. I don't know what this is about. Obviously. Okay. So you are phase 2. What are we doing in phase 2? Oh, you're training it with different approaches. You've got multi-phase training. All right. I've not ever needed to do this before, but you can make it. How's it going there? Annie, hit the input only the last 8 samples. Got it. All right, so you're only going to grab the last 8 samples, and then you're going to continue on with a different, slightly shift, average, normalize. Okay. All right. And this is right. This is the function that's inside your other functions. Okay. Looks good to me. All right. Update predictor. All right. That's just normal stuff, I think, from there. Although this looks different. Build only new training window. This is like just a complete shift away from what we were doing earlier. So it's kind of neat to walk through it to see what you've done. Essentially, you rewrote the whole thing, other than the visualization. That's it. You rewrote it all, Neva. You wrote it all. It's kind of crazy. All right, so unified AI pipeline, update predictor, input coordinates, fit recent. Okay. Least, predict newest. Optimization on what you had earlier, otherwise the same. Yeah, I would say it's an optimization. Like just a little bit of an optimization. Like it's like a full new model and a whole new approach with various optimizations. It's pretty great and it works really well. You can see the result. It's fantastic. I really like to see this. This is great. It works very well. For the most part, it works very well. Coordinates. Okay, so now we're just doing the regular prediction. And then the rest. See, this part right here. That's all the same right there. That's only like 100 lines of code. You added like 500 lines of code. You made a whole, well, I mean, a lot of it's double. So like you've got a whole section here like that's commented out. Did you use AI to improve it? No, like that function is exactly the old version of how you gathered input. Yeah, it is. Yep. But I'm not making a new array every time. Got it. Okay. Yeah, sounds good. Right. We didn't have enough data. We need more clicks. So fundamentally, we are basically trying the smallest network we can get away with. We ideally want to not require too many examples before we can start training. Makes sense to me. This naturally means that we want a convnet, a convolutional neural network, and a linear output for the regression, for the click prediction, as they work great with small amounts of parameters. Hey, there we go. Also note that this is continuous training, so we need to keep the network elastic. Okay. And now we're going to learn about elasticity. Let's go here. Let's go. All right. So let's learn about some elasticity here. After playing around with a lot of models, I noticed that they can sometimes get stuck on particular patterns. Yep, they like find a pattern that works and they get stuck there, and they might not learn other patterns. Sigmoid activation has a nasty tendency to have a vanishing derivative on these edges, and thus we are using no activation. I mean, I saw ReLU in there, but ReLU isn't necessarily an activation. I mean, it just sort of, it's a clipper, right? All it does, it clips at 0, right? That's all it does. So kind of an activation, but not really, which means we can predict clicks off screen, and it's worth it. Another issue is if we at any point 2.2 neurons have the exact same weights, they would stay the same forever. Really? I didn't know that. That sounds like a problem. This gradually leads to them being locked forever and a model effectively having one less neuron. Also, if something goes very negative into the ReLU, we get those dead neurons. Yep, because it's 0, because it stays 0, right? The derivative is 0 and it stays 0. So it's gone forever with the ReLU. Try to solve both with weights and random movement by giving small noise to the gradients, which means that takes care of the zeros. That's pretty neat. We also add dropout to encourage neurons to be different. Okay. Here we go. Skip connections. Here's the skip connections part. We're learning about the rest of what Neva wrote here. Note that a lot of the times a click is directly related to the input. So adding that to the last prediction head does wonders. It makes a lot of sense, right? We want to have a time series, right? We need to represent adding that to the last prediction head does wonders. In general, because we want training to adapt quickly, we want the least amount of distance between each weight and the cost. The network is aggressively optimized to be short in terms of layers. Okay, so there's not very many layers. That's something that we noticed. I saw some conv layer. I saw a linear layer. And was there anything else? Sequentials here. Yep, a conv and then a linear layer. And then one more linear layer right here. So I just saw just 3 layers. It's not a lot, right? Can this be optimized further? Probably. Can it be simplified? I don't know. It's actually already a fairly simple model. As you can see here, there's very little in terms of the model itself. There's just a lot of manipulation on the input to the model. That's where the majority of the code is focusing on getting the data the right shape as it is entered into the model, which is the most important part, I think, right? It's a critical aspect to AI, getting the data in the right shape. Otherwise, as you can see here, very simple model. There's only 3 layers. I'd probably sit on more stuff with the architecture.